Lisa. She only played one night stands now. She was a day. It's linear algebra. And we're going to Anki right now. Is day tripping relevant to linear algebra? What a deep philosophical question. All right, no Anki flashcards here today. So we'll jump right into what we reviewed and learned yesterday. Well, we learned back substitution. That is the method in which computers will likely solve partially solve linear systems and augmented matrices because it's more efficient for computers than Gauss-Jordan. Back substitution, you'll do Gaussian first, and then you'll do back substitution, whereas by hand, you'll do Gauss-Jordan typically. Okay. That's something we learned. What else did we learn? How to do back substitution. How do you do it? Well, first you get into row echelon form, right? Because that's Gaussian elimination. Get the row echelon form. Then you're going to basically convert the augmented matrix back into the equations, right? And then you're going to go from bottom up, substituting, or you're going to actually solve for leading variables in terms of the free variables, then go from bottom, lowest equation, substitute that leading variable into the above equation, and then take the leading variable of that equation and substitute it for the one above it, and that's called back substitution. Eventually you get to the top equation, and you can write the parametric equations, and shut bada bang, bada boom, there you go. I think that's it. Yep. I got one question, that is do you need to write every equation in the system when writing the final parametric equations? Okay, that's just a question to answer later. The question popped up. What else we got? We learned, so back substitution, what it is, when to use it, how to do it, and then, how to determine number of solutions based off of the row echelon form. Or is it reduced row echelon form? Row echelon form, I believe. Basically, if the bottom equation in row echelon form is zeros, and then there's something in the rightmost column that's a no solutioner. If there's a leading variable in each variable column, then it's going to have one solution, and then if there's free variables, essentially, if there's free variables, and the system is consistent, meaning that the bottom equations are all either zeros or there's no zero rows, but never having like the 0, 0, 0, 0, and then the rightmost column having something, that's the no solution. If it's not that and has free variables, then I'll have infinitely many solutions. So I think that's, no, not quite. Before I look at what we did yesterday, we also started reading a section called Some Facts About Echelon Forms. So we learned about 3 facts so far. Okay, yeah, there's actually a bit more. All right. Right. Here's the first fact. Every matrix has only one reduced row echelon form. Second fact. Row echelon form, however, is not unique. You can have multiple different row echelon forms for the same matrix depending on the elementary row operations you utilize. Okay? Then the third fact is what we're working on. We didn't get all the way through. We had a bunch of definitions, pivots, pivot points, pivot columns, pivot rows. Here we go. Basically, even though there's only one reduced row echelon form and a ton of potential different row echelon forms, maybe infinitely many row echelon forms, they all have, well, they all have the same number of, non-zero rows, I believe. And they also have the same locations of the leading ones. And the leading ones are known as pivots in these forms, in row echelon form, reduced row echelon form. They're known as, the positions of the leading ones are known as pivots. Columns that contain leading ones are known as pivot columns. Rows that contain leading ones are called pivot rows. And then we were talking about pivot positions, where you substitute something. That's where, let's check and then we'll continue. Make sure we got everything. Back substitution. Hand versus computer. Yep. Yeah. Right. Determining number of solutions based from the reduced or from the row echelon form. Every matrix has one RRF. One has more than one ref. Or refs are not unique. Okay. Boom. I actually got 3 right. Same number of 0 rows and therefore probably non-zero rows. Yes. And positions of leading ones, pivot positions. Okay, no. We learned the pivot positions are the locations of the leading ones, not pivots. We haven't learned what pivot is yet. Pivot column, right? Pivot row, right? We just need to learn what pivot is now. So I'll be back after I finish this section, which should be just a few seconds. Let's go, guys. That's the section. Okay. Pivots. Pivot positions are the locations of the leading ones in an augmented matrix when it's in ref, that is reduced, or that is row echelon form, and RREF, reduced row echelon form. Pivots, however, instead of pivot positions, pivots are locations of these pivot positions. Non-zero entries in pivot positions, but we're not talking about, it doesn't have to be in reduced row echelon form or row echelon form, just the normal matrix at the beginning. The boxes where the leading ones will be, if it becomes row echelon form or reduced row echelon form, those are the pivot positions. Cool. Here we go. Final section of 1.2, reading. Round off error and instability. I'm actually really hyped about finishing this, so I'm so excited to get into the actual practice problems. All right, I'll be back in a sec. This final 1 paragraph section. Round off and instability. Round off is referring to this thing where computers typically round off solutions and steps and numbers, which leads to basically instability or something being unstable. If you have a round off error that compounds, this gets rounded, then this gets rounded, then this gets rounded. If you do enough operations, eventually it becomes basically an answer that's useless. So unstable is referring to algorithms in which that occurs. And Gaussian elimination has about 50% less operations on average than Gauss-Jordan elimination, and that's why computers opt for Gaussian elimination and back substitution rather than Gauss-Jordan elimination to minimize round-off error, right? And they just kind of said this will be addressed more in Chapter 9, and that there's sometimes a gap between theoretical math and actually like applying and doing math, especially with computers, with this round-off error and instability. But that's it. That is it. Finished reading Chapter 1, Section 2. Amazing. Let us now start doing practice problems. So I'm gonna start doing practice problems, and I'll be back at the end of the day to reflect and call it a day. All right, that's it for today. The timer just went off. We're actually doing like the stuff now. We're solving an augmented matrices, which is pretty cool. Identified reduced row echelon form versus augmented, or neither. Identified pivot columns and rows, and then solved. And then we're working on solving another one using Gaussian elimination. So, I just stopped mid-problem. We'll have to finish that tomorrow. And then at some point I'd like to start interleaving problems from 1.1. But I mean, at this point, we can probably just keep moving, do one pass through, and then go and start doing interleaving maybe. Yeah, I think that's good for today. I will talk to you guys later. See ya.